to have an exam? No. Because now you will have the second part of the course, and then the third part of the course, and only after that they will have the exam. So the exam will not be before, I think before May. So you have some time to study this. And also something else. It's since the three parts of this course are treating essentially the same problem, but from different point of view. This will if you study all together from these different points of view, it will be much easier and much more complete. So other people are here. Oh yeah, Aminat. Hi, Aminat. Alejandro.
Hi, Professor.
Hi. Grace.
Hi.
Who is Grace? Can you show me your picture? Amelia. Grace. Hi, Grace. How are you?
Hi, Professor. I'm fine. How about you?
Okay, thank you very much. And Amelia? Amelia. Hi, Amelia.
Hi, Professor.
Hi, how are you?
Fine, thank you.
Did you go skiing? I already asked the people, but nobody, the people said usually that they don't go skiing. It's because you don't have ski, or you don't like skiing, or there is no snow at your place.
Sorry, what?
Okay, don't worry. So, okay, so let's start. Can we start? Are you ready? I don't remember because it was a long time ago, more than a week ago. Did we talk about the communication between the Mediterranean and the Atlantic? You remember that? So we did or we did not?
I think, yeah, we saw that.
You saw this slide? This one also?
Yes.
This, huh? Okay. This thing you saw. But I think that we didn't talk about the variations of the global ocean circulation. And the global ocean circulation, as we were talking before, is this one thing, this thing here, and here is this how it looked like, and we have mentioned the fact that due to the changes of the oceanographic characteristics in the northern Atlantic, the intensity of this world ocean global overturning circulation might be changing in its intensity, because the engine which is here can change. It can change. Why? It can change because of the possible heating of the surface here in this area here, on one hand. On the other hand, because of the melting of the polar ice, of the Greenland ice in this area here. The two things, as we mentioned, the two things can act in the same direction. They can stabilize the water column. By stabilizing the water column, it would need more energy to overturn, to change, to mix vertically the water column. So the long-term climate change may may influence the intensity or the efficiency of this engine which drives this global overturning circulation. And that's the cross section at the latitude of 26 degrees, which shows how it looks, this global overturning circulation, how it looks like at that 26 degrees north. You can see the Gulf Stream, which runs northward in a surface area, in a surface layer, and it runs northward. And then there is the engine which drives, which generates the dense water, which then flows down in deeper layers and then goes back in a western array in a deeper below this Gulf Stream. So the warm water essentially goes northward, and the cold water below this warm water flows southward. But not only that, there is also another thing, is that the Gulf Stream and a huge amount of water which flows northward has to be in a surface layer, has to be compensated by the southward flow all along the width of the Atlantic Ocean. So there is this small amount of water which flows down, but very slow, and this compensates for this huge amount of water which flows northward. So if you want to control the control of the intensity of the northward flow, can be easily done by doing measurements, for example, along this 26 degrees north. And this is what, in fact, the people are doing. They put a number of moorings which have sensors which measure the currents along this transect. So you can see that here in this specific case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, around 16 arrays which are measuring the meridional flow, the northward or southward flow. What this helps us, what this we would need for this measurements we need to determine the intensity of the north-south exchange, or the meridional exchange. And this then would tell us how the circulation is changing on the long time scales. This obviously, to understand the changes, we have to do these measurements for a long time. Yeah. So we have to do these measurements for a long time, and these measurements for a long time then would give us the information of how this meridional circulation, how this north-south circulation changes on the long time scales. Unfortunately, these measurements started in early 2000, so we have only around 20 years, 2 decades of these kind of measures. From the climatic point of view, this is not really enough significant measurements from the point of view of the time scale of these measurements. Anyhow, so that's where we did the measurements. Oh, here are the measurements what we are doing. And so as we can see, it says here, direct measurements of the AMOC, this is the Atlantic Meridional Overturning Circulation, only began relatively recently. A line of sensors between the Bahamas and the Canary Island called RAPID was installed in 2004. You see, 2004. A second sensor array spanning the North Atlantic from Canada to Greenland to Scotland, called OSNAP, went live in 2014. So this is the northern part of these are the measurements of the northern part of this AMOC, the Atlantic Meridional Overturning Circulation. And as it says here, as I told you before, neither project has operated long enough to produce clear trend as the people would like to. And so there are also these measurements also reveal the system of currents which are much more complex than one envisioned. The variability of currents are much stronger and much complicated and complex than it used to be thought about. So this is that's the so we have here here, for example, that's one thing why we should expect the changes of the AMOC of the Atlantic Meridional Overturning Circulation is that the Greenland ice sheet, which is melting at the upper end of projections, is about 6 times faster than in the 90s. So subpolar North Atlantic recently became less salty than at any time in the past 120 years. Obviously, if you are adding the fresh water, which calm the ice melting, then the surface water becomes fresher. But there are also anyhow a little agreement on the cause. Changes in wind patterns and current may be contributing as could the greater rainfall. So the freshening of the surface water in the Atlantic can be also caused due to the different wind patterns, can be also caused to the rainfall. And so, but according to some some studies of like 13,000 years ago, meltwater from Greenland is beginning to slow the AMOC. So the main cause of this slowing down of the AMOC should be or could be the melting of the Greenland ice. So that's something with it. And there is one interesting paper in Nature in 2018. Scientists presented paleoceanographic, so evidences of the old times, the deep convection of surface water in the North Atlantic, the engine that keeps in constant motion, began to decline as early as 1850, probably due to increase of freshwater influx from Arctic ice that had melted at the end of a relatively cold period called the Little Ice Age. Because the Little Ice Age is the period before 16th, 17th century. And this period was relatively cold, and this is called also Little Ice Age. After that, the temperature started to increase, and then there is around 1850, the AMOC, according to some studies, started to weaken due to this melting of ice, due to the increase of the vertical stability of the water column. And so that's how it looks like. And what these are the, however, fortunately, the measurement started only in 2000, in the early 2000. Therefore, we have a very, very short time series. And here is how these time series look like. This is the measurements from the very beginning of these measurements. Fortunately, I have the times, the graph. We started 2004 when all the measurements started, and ended up in 2014. This is one part of the time series because the measurements continues after 2014. What one can see is that the currents, these are the current or transport. This is the transport. You see, this is the transport in Sverdrup. Sverdrup is one Sverdrup is equivalent to 1 million meter cubic per second. So you can see that the transport going from 30 to 20 millimeter cubic per second, and then in this very specific period, there is a clear trend of decrease of this transport, and but this red line is the smoothed graph of this time series, which is these peaks, very strong peaks on very high frequency. And so the structure of this current, or the temporal variability of this current, is rather complex, or shows a rather strong temporal variability. Nevertheless, another thing is that there is a trend of decrease of this transport. We started at around 15, 17 millimeter cubic per second and end up at about 14, 15. So there is this, in this very specific period, in 10 years, there is a decrease of the transport for about 2 millimeter cubic per second northward. But and in fact, this paper presenting these results has been published in a very important scientific journal, which is called Science, where the authors, they sustain that that they have evidences of the long-term decrease of the global ocean circulation, of the Atlantic Meridional Ocean overturning circulation, which then has been shown later. Adding up the newest data, it has been shown that it's not really a trend of decrease. It's a long-term variability. Therefore, here you can see how important it is that if you do your measurements, and you have to do your measurements on a time scale enough long that you are able to describe the variability. Because here, from here, if you have such a short time scale, relatively short measurements, then you will say, okay, there is a decrease. But the natural variability of this specific time series is much larger than 10 years. And therefore, we picked up only a piece of it. And from here, we come up to a wrong conclusion that there is a decrease. But it's simply long-term variability on the time scale of 20, 30 years. So anyhow, these are the first results which have shown, and the measurements continue, and the important observation should continue, and important conclusion from that should be obtained from. This is one interesting graph which shows it seems complicated, but it's not very complicated really. This is that's the North Atlantic temperature anomaly, 15-meter depth, average for May and July 2010 at the end of 2009, 2010. So what you can essentially see that in this central part, which coincides with the Gulf Stream, there is a decrease there is a negative anomaly. Negative temperature anomaly means that the sea surface is cooling. Why is cooling? It's cooling because there is a weakening of the Gulf Stream intensity. So it's a weakening of the transport of heat northeastward. So so this is an illustration how important is the intensity of the northward transport. As soon as we have the reduce of intensity of the northward transport, we have the decrease of the sea surface temperature, which then we will see later, which then reflects on the changes of the climatic conditions. And in fact, indeed, that's what we would like to end up with. The impact of for Europe from shutdown of the meridional overturning circulation will be a reduction in runoff and water availability in southern Europe, major increase of snow melt, flooding in Western Europe. Then there will be increased sea level rise on the Western European and Mediterranean coast, because we will be adding up the fresh water. reduction in crop production with impacts on food prices. There will be since there is a reduction of runoff and water availability, there will be a reduction in crop production, and obviously this will end up with an increase of food prices. There will be changes in temperature affecting ecosystem in Western Europe and the Mediterranean, affecting biodiversity, forest products, and food production. So the changes in temperature and automatically is felt at the ecosystem. And there is another aspect, which is then it's a higher level response, is disruption to winter travel opportunities and increased icing of northern ports and seas. So this will bring the difficulties in transport in northern ports and seas. Then there will be changes in the regional patterns of increase versus decreases in cold and heat-related deaths and ill health. This is something which will end up in generating problems with the human health. There will be a movement of population to Southern Europe, because Southern Europe will have more moderate climate than the Northern Europe, which will have even more severe climate. And then it will need to refurbish infrastructure towards Scandinavian standards, because if you have the people from Scandinavia coming to Mediterranean, they have different standards, so you have to refurbish infrastructure for them. So all these points were shown here, and they will be bringing the strong changes in attitude, in a way of life, at the end, in food production, in health, and so forth. These are the whole series of impact from shutdown of the meridional overturning circulation, or of the changes of the climate in Europe. Okay, I will not say about this thing anything, so because you will have this, so let's see whether I think this is one more thing what I would like to just to mention to give you an idea what are the response of the climate to climate change, or that's another important aspect of the climate change, which is a relationship between extreme events and the climate change. What are extreme events? Extreme events are tornado, are flooding, all these meteorological conditions which are on a short time scale, because climate change is something which happens on a long time scale, changes on a time scale of tens and hundreds of years. Extreme events, on the other hand, are happening on a short time scale, on a time scale on the order of a day or even or weeks. And these are they will be changed due to the climate change. Here, this kind of problems, this kind of extreme events like this one, these are the consequences of the Katrina tornado in 2004, I think, if I'm not wrong. And this kind of events, the frequency of tornado will be increasing and will be becoming more and more frequent. And here is how it looks like. So you can see this is the Gulf of Mexico. This is Florida, Cuba, Mexico, and this is that's one of the tornadoes. This is a very specific case. This is that's the Katrina tornado. So you can see that the tornado are, as far as the time scale, are very short. On the time scale on the order of days, and they are also small. They have very small spatial scales. They are on the spatial scales on the order of 100 kilometers. And they are anyhow connected to the long-term climate change. Why? Because the increase, for example, of the sea surface temperature, what makes us in the atmosphere, lower atmosphere becomes unstable because the lower layer of the atmosphere becomes warmer than the upper layer. So the atmosphere becomes unstable and results in a more frequent formation of tornadoes. And this is one of the example, the most dramatic example in the last 20 years of a tornado and its influence on a life. And if we go to see the number of systems in the last 2015, these are the number of connection is not stable, but I hope it is. Since you don't say anything, it's okay. And you can see from here that the number of systems shows a slight trend of increase with time since 1850, since the time when we had the statistics of this system until today. So you have different grade of these hurricanes, of these tornadoes, which are storms, hurricanes, or major hurricanes, and you can see for all these colors, major hurricanes, you can see that they increase with time. As the name storms also the increasing in time, or hurricanes are showing the trend of increase. Therefore, this is something what can be associated again with the climate change. The other thing is that again we are talking about the short-term events or shorter-term events, which are probably associated to the climate change, are the winter droughts. Winter droughts are the periods when the rainfall is lower than average in a certain area. Here we are talking about the Mediterranean, and you can see these statistics. This is the winter droughts statistics from in the last 100 years, 110 years. And for the red part means that the rainfall is lower than average, and this green part means that it's higher than average. What you can see from here is that there is a continuous decrease. It's a decrease, or especially in the last 30 years, there is a very few situation in which the rainfall is above this average, while in the period of 1990 to 2000, 12 driest winters of the last 110 years were recorded. These winters are the driest winter in the last 110 years. So you can see that there's a certain acceleration of the occurrence of the winter droughts in the Mediterranean, which is something what has been also, if you remember the graph, which or consequences of here it is increased sea level rise, reduction in crop production with impact on food prices, reduction in runoff and water availability in southern Europe. That's what are one of the impacts from the shutdown of the Mediterranean overturning circulation. And indeed, and this is what we see here. We see the increase of the frequency of the winter droughts which might be associated to the might be associated to the reduction or weakening of the Atlantic meridional overturning circulation. What is the overall opinion of the climate scientists about the climate warming trends? Not everybody obviously believes in climate warming trends, not from the point of view of the whether they exist or not. The climate warming trends have been evidenced. There is no doubt about that. But some of scientists are of opinion that they are not due to human activities. And however, about 97% of climate scientists agree that climate warming trends over the past century are extremely likely due to human activities. So the human activities are, according to majority of scientists, are due to human activities. Only very little percentage of them do not believe in that. As any other thing, no, not everybody believes in what the general opinion is. But anyhow, exists almost as very good opinion. Exists the uniqueness of the opinion of the entire community of climate scientists that the climate warming trends over the past century is due to human activities. Okay, so that's what I wanted to tell you about let me see now, about the climate change. And now we will pass through, we will go to another part, which is let me see where I am. I have to find now we are now passing to instrumentation, to oceanographic instrumentation. And the rest of our course we will be spending to studying the instrumentation for physical oceanography instrumentations. Let me do now oh, can you see my screen?
Yes.
Very good. Oh, this time I'm very good. Okay, so we will be talking about the physical oceanography, instrumentation of the physical oceanography. And so we will be talking about number of instruments, number of trying to go from the I will give you the historical overview of the evolution of the physical oceanography instrumentation. This is something which is very important in the sense that the better temporal and spatial resolution of our instruments. Spatial and temporal resolution, I mean the how fine is the distance between the two measurement points, or between two moments of the measurements are. How our description of the phenomena depends on that. The better is spatial and temporal resolution is the more phenomena we are able to record, to observe. So it's this is we have to respond to a number of questions. Why and how to observe and study the oceans? Why and how? Why? We have seen just already in some previous slides and previous parts of the course that, for example, to study the AMOC, the Atlantic meridional, overturning circulation, we have to have a certain whole series of instruments which measure continuously. So in order to respond to this question, why and how to observe the study of ocean, we have to know what we are going to study. Then we will talk about the physical oceanography observation, research and societal needs, types of platform and measurements, and then we will talk about the observation with classical instruments. Physical oceanography is, between other, is one experimental science, and requires observation and exact measurements to achieve its aim. It can draw on the experience of the related science field in physics and chemistry and make use of existing achievements in the areas of technology and engineering, because the technology and engineering help us to develop different and more efficient and more advanced instrumentation. But the oceanic environment places unique demands on instrumentation that are not easily met by standard laboratory equipment. Why? Because, you know, the ocean is salty, and one of the things, the ocean is salty, you cannot, and the salt water acts, has a very distracting action on instruments, on metal and so forth. Therefore, this is one of the very important things. As a consequence, the development and manufacturing of oceanographic instrumentation developed into a specialized activity. Manufacturers of oceanographic equipment serve a small market but aim at selling their products worldwide. So I will give you an overview of the range of instrumentation C and the principle involved. It aims at covering standard classical instruments as well as model development, because as you have seen in one of these slides, you have seen that classical instrumentations were such that the measurements require that to have a ship. It requires to have a ship that to be stopped at a certain place and do the measurements. All this is time-consuming activity. So as a consequence of that, the measurements and coverage of the larger area were very difficult to achieve. And a research and the table which shows that what are the equipments and what we use. We have research vessels, we have moorings, we have satellites, submersible, towed vehicles, floats, and drifters. So these are number of instruments, number of equipment and instrumentation which are used to measure, starting from a research vessel where you need the human crew, you need the permanent presence of men on the research vessel, and then if you go further, sorry, you don't need the presence, the continuous presence of men. New moorings, which are, you will see later what, satellites, submersible towered vehicles, flows, and if they don't, all of them, they don't need the presence of men. Measurement done. Then we have to know what we are going to measure, what parameters we do measure. We measure hydrographic properties, so that means the parameter of state of the ocean, so that means temperature and salinity, in order to obtain the density, which is essential, as we have seen before. We need the measurements of hydrographic properties, such as chemical parameters like oxygen, nutrients, and tracers. All these are chemical, they need the chemical methods. We can measure also the biological parameters, which are in this specific case, as we are talking about physical oceanography, are used as a tracer. You remember when we were talking about the dense water formation, that we've looked at the density of the chlorophyll in the surface, which has been used as a tracer of the dense water formation. So in that specific case, for us, for physical oceanographers, the chlorophyll has been used as a tracer. Obviously, chlorophyll being a biological parameter is also used by biologists in order to understand what is the spatial distribution of the phytoplankton biomass over the world ocean. Then we have the measurements of dynamic properties. So that means the velocity, current velocity, waves, sea level, and mixing processes. And these are also, they need to have a specific instruments. So we have measurements of hydrographic properties. For that, we need the thermometers. In this specific case, the classical instruments are reversing thermometers. You will see later on what are they. Nansen and Niskell bottles are the bottles which are used to pick up the Diggs samples in order to determine oxygen, nutrients, and tracers. We use the XBTs and Ctds. These are the instruments which are used to measure temperature and salinity, but by automatic measurements. Then we have multiple water sample devices, which are essentially doing the same thing as Nansen and Niskell bottles for picking up the instrument, the samples. We have a Salinograph, which is the instrument which is installed on the ship, which is used to continuous measurements or at a certain depth of the temperature and salinity. And then we have remote sensors, which are used to measure the various hydrographic properties like temperature, tracers, salinity. Recently, they developed the salinity measurements from the satellite, so we have the whole series of measurements. Then we have measurements of dynamic properties, for which we use current meters. Current meters are, as the name says, measurement of the currents. Wave measurements, these are the measurements of the sea surface changes, but wave measurements in this specific case means the high frequency waves, the wind waves at the sea surface. Then we have the tide gauges. Tide gauges are used to measure the tides, the long-term, the diurnal and semi-diurnal variability of sea level. So you can see that here you have, on one hand, you have wave measurements, which is the wind wave measurements. And on the other hand, you have the measurements of waves, but long waves, which are tides. Then we have remote sensors. Remote sensors are used to measure the sea surface height, sea level. Then they are used also, if we consider this as also the meteorological parameter, to measure the wind. And the wind is important meteorological, but obviously also the oceanographic parameters, because the wind influences the currents, as we have seen before. So in order to obtain the interaction between air-sea interaction, we need to have a very good knowledge of the wind field. And then finally, there are shear probes. Shear probes is the probes which are measuring the vertical variability of currents with depth. Okay. So we have six types of measurements. Or we have different types of measurements. We have direct measurements, which are temperature with Ctd and XBT, current meters, flows, and drifters. So that means that your instrument, whichever it is, has to be in the sea. So these are the direct measurements. So you cannot do the measurements from outside. Indirect methods are the methods where you are measuring from satellites, from ADCP. You will see, we will be talking about ADC, the Acoustic Doppler Current Profiler, HF radar, high frequency radars to measure the sea surface currents. Then we have a salinity with Ctd. Then we have in situ measurements, which are for current meters, floats, drifters, gliders, research vessels, CTD and XBT. These are all in situ measurements. But we have, as opposed to that, we have a remote sensing. We have the measurements from the instruments which is not necessarily at the same place where it measure. Satellite is certainly not in the sea. ADCP, acoustic Doppler current profiler, is not measuring at the place it is. It's measured from some other place. HF radar, the same thing. Then we have two types of measurements. One is Eulerian and the other one is Lagrangian measurement. Eulerian measurements means that your instrument is fixed in the ocean and the current passes by. So you have the continuous measurements of oceanographic parameters at a single point. You measure currents, you measure temperature, salinity, you measure this thing. And these Eulerian measurements has been done or by current meters which are fixed, by a research vessel which is anchored, and then do the CTD or XBT measurements. We have moorings which are on a mooring line, where you have current meters, temperature, and so forth, and ADCP. So all these instruments are fixed at a certain geographic position. Lagrangian measurements, as opposed to that, are those measurements which has been done by instruments which are moving with currents. So we have floats, profilers, and drifters. These three types of instruments, they are measuring whole series of oceanographic parameters like temperature, salinity, chlorophyll, nutrients, and so forth, but not at a single point, at a fixed geographic position. But it's do these measurements by moving with the currents, okay? So these are two different kind of measurements, and you cannot compare completely these two types of measurements or integrate these two. You can integrate by doing some important assumptions. And here is the research vessel. That's the research vessel. This is like any other ocean-going ship. Research vessel has to meet the requirements to be seaworthy and capable of riding out the bad weather. So that's essential for oceanographic ships, because they have to be anchored and they have to stay at the sea with a very severe sea and weather conditions. This is the one thing. Additional requirements such as handling of heavy equipment at sea or the need of a large scientific party during an interdisciplinary study can increase the minimum size. Typical ocean-going research vessel is 50 to 80 meter long, have a total displacement of 1,000 to 2,000 tons, and provide accommodation for 10 to 20 scientists. So between 10 to 20 scientists can stay here for a certain period of time and go on oceanographic measurements. What they do is this ocean-going ships, research vessels, they go from one position to another. They stop, they anchor, and they lower their instrumentation, do the measurements, pick up the samples, and do the analysis already at the ship. And for this thing, the ship has to provide accommodation for 10 to 20 scientists. And this is one of the oceanographic ships of our institute, and that's OGS Explorer, which has been used for polar studies. And here is how it looks like the one part of the ship, and most research vessels have an endurance of 20 to 25 days, which that means that they have autonomy to stay at the sea 20 to 25 days without entering the harbor. So this gives them a range of 6,000 to 8,000 nautical miles, sufficient to operate at the high sea within a few days of reach of land. Only major oceanographic institutes of the world operates research vessels with global research capability. And in fact, if you remember when I showed you the one of these first slides, when I show you the world coverage of the world ocean, the coverage of the world ocean by oceanographic studies, they have been done with this kind of ships. So the ship would start from harbor, do its measurements along the transect, will stop in any at each position, what we call station, do its measurement from the surface to the bottom, and then go to the next station. So it will used to be like a month of a passage from one part to the other part of the Atlantic, for example. And this is how it has been done. And now we let's talk about how the classical measurements of hydrographic properties has been done before before the construction of the automatic instrument. This is then a reversing thermometer. A reversing thermometer is in its upright, not reversed position. So the mercury, when this instrument is in the sea, when this instrument is in the sea, it measures the temperature. It goes up, you know, obviously. The thermometer is reversed. The mercury column ruptures at the appendix of the capillary section between the red and blue, this thing here. The red and magenta mercury settles into the upper reservoir while the cyan mercury returns to the blue reservoir. The level of the magenta red mercury can then be read against the scale and indicate the temperature. So essentially what is happening that this is cut here and the temperature remains recorded. The green thermometer, so you have a cyan, and the green thermometer is an auxiliary thermometer, which gives the ambient temperature. It is used to check the temperature when the main thermometer is read on the deck. Because what you do, for example, you lower your thermometer at 1,000-meter depth. When you take it out, you are measuring, you are reading this recorded temperature at the surface. You are reading in another environment temperature. Therefore, you have to take into consideration this. You have to correct the red temperature in cyan due to by reading the green thermometer, which is auxiliary thermometer, which gives the ambient temperature. Therefore, you have to reduce these the reading of the cyan part of the reversing thermometer. And here, the overall accuracy is therefore achieved is 2 times 10 to the minus 2 grade centigrade. So that's the thing. And here is something what we call Nansen bottles. What is Nansen bottle? Nansen bottles, we don't need only to measure the temperature. We do need also to pick up the water samples. Why do we need the water samples? We do need the water samples for determining the salinity, because at that time when they used to use these reversing thermometers, the salinity has been obtained by doing the chemical analysis. Therefore, at the depth, for example, 1,000 meters, not only you measure the temperature by reversing the thermometer, but you have somehow to pick up the water at that specific depth, and you do it with these Nansen bottles. These are the metal reservoir of typically of a few liters, and here you fix your reversing thermometer, and when it comes to a certain depth, to 1,000-meter depth, for example, there is a messenger. You can see there is a messenger where you leave it from the ship. It goes along the rope, and then give a push to the head of this reversing thermometer, to the Nansen bottle, and it reverses. It reverses and it closes, at that specific depth, picking up the water at that depth, and also recording the temperature at that depth, because not only that the Nansen bottle has been reversed, but also the thermometer, which is fixed at the Nansen bottle, has been reversed. Therefore, you have on one hand, you have the recorded temperature. It's a very ingenious creation, and you have also the sample from that specific depth. And this sample can be you can pick up the water not only for salinity. You can pick up the water to do the analysis of oxygen, of chlorophyll, and so forth. All the component which needs the specific analysis on board of the ship, you can pick up from that specific Nansen bottle. But then we have something which is called the Niskin bottle, which is a much larger volume. It's plastic, and you do essentially the same thing. You lower the Niskin bottle to a certain depth. You pick up the water. Your reversing thermometer again is reversed, and then you essentially, as far as the reversing thermometer is concerned, do the same thing. So that's the Niskin bottle. This is further evolution of these. But then we come up, there is the era of Ctds. These are the today's standard instruments for measuring temperature, salinity, and often also oxygen content is the Ctd, which stands for the conductivity, temperature, depth. It employs the principle of electrical measurement. So you see, before we have a mechanical action on Niskin, on Nansen bottle, and we pick up physically the sample and bring it to the surface. Here we have the principle of electrical measurements in situ, measurements at a given depth. And we have the platinum thermometer changes its electrical resistance with temperature. It is incorporated in an electrical oscillator, and so for the conductivity of seawater can be measured in a similar way as a frequency change of a second oscillator. So we have essentially electrical measurements of temperature and conductivity, and the combined signal then, which is there measured in situ, is sent up through the single conductor cable on which the Ctd is lower. So you practically have a continuous measurement from the surface to depth you want of the temperature, salinity, and depth, the pressure. So this produces a continuous reading of temperature and conductivity as a function of depth at a rate of up to 30 samples per second. So every 2 seconds we have a couple of temperature salinity measurements. So this is the enormous improvement with respect to bottles, to Nansen bottles, where we typically have the 12 Nansen bottles from surface to the deepest layer. So we have 1,000-meter depth. You have to distribute these 12 Nansen bottles on these different depths, where obviously, since the oceanographic properties are changing much faster in a surface layer, you put more bottles in a surface layer and more distance water bottles in deeper layers. Here you have the continuous spatial resolution with Ctd, and you measure the temperature and salinity every 2 seconds, one sample. So if you go with that, if you lower your instrument with 1 meter per second, then you have the measurements in 1 meter. You have 30 samples, which is much stronger, higher resolution that it used to be a nonsense bottles. There are also multiple measurements of hydrographic properties, multiple water sample device. That's another thing. Here you use the multiple sample device. What do you use multiple sample device? You use it if you want to, because with CTD you can measure only temperature and salinity. If you want to do the picking up the samples at different depth, then you have to have the higher vertical resolution, and then this is another further step ahead with multiple water samples. What you have typically here, you have 24 Niskin bottles, which you lower into the sea, and they open at different depth, and they close at different depth. They pick up the water sample at different depth. When you bring it to the surface, then you pick up the water from there. You use this in the bottles, and then take it to the laboratory and do your analysis: chlorophyll, chemical analysis, oxygen, nutrients, whatever you want. You do these measurements with this thing. And then we have a thermosalinograph. The thermosalinograph is practically the introduction of a CTD. Opened the possibility of taking continuous readings of temperature and salinity at the surface from using the cooling water intake of the ship engines, which is pumped through a tank in which a temperature and conductivity sensors are installed. So what is happening really, that you pick up the water from the sea. It passes through the CTD and goes into the system of the ship. And here you measure the temperature and salinity in a continuous way along the ship path. Yeah, that's something which is also gives you very high resolution of temperature and salinity distribution along the ship track. ESP-PDOs are expandable batic thermograph, which are the instruments which are expandable, so you throw them into the sea, and the oceanographer were using those instruments for many years to obtain information on the temperature structure of the ocean to depth up to 1,500 meters. You can imagine that this is not a very that's not very ecological measurements, because these are expendable. So you throw into the sea, and this leaves stays at the bottom of the sea. So for some time they were used pretty much, but now they are not used anymore, hopefully. And here is what they do. You know, you throw this into the sea. It is connected with a small. You drop the instrument, and then it records the temperature from the surface to a certain depth. Then it's this is one record, and that's. Now let's go to measurements of the dynamical properties: currents, waves, and sea level. First of all, current meters. Ocean currents can be measured in two ways. An instrument can record the speed and direction of the current. That's just what you have to know. Or it can record the east, west, or north, south component of the current. Both methods require directional information, and all current meters therefore incorporate a magnetic compass. It has to have a compass in order to orientate the instrument. And then we have, and then it has to measure somehow the velocity. And the velocity is measured by mechanical, in specific case, mechanical current meters use a propeller device, and to measure the current speed. So the number of rotation is proportional to the velocity, while the current direction is determined by the orientation of the vein. Okay, so that's it's very simple. I shortly explain the classical methods of current meters. Then there we have current meters, which are the current meters use two propellers with cosine response at 90 degrees. These are mechanical current meters, which may measure current speed by counting propeller or rotor revolution per unit time, and current direction by determining the vein orientation. So here is the propeller, you see, here is the propeller, and this is the vein. So counting number of rotation and determining the orientation of the vein, you determine both direction and the magnitude of current. And you put this typically, you moor this instrument in the sea, and you leave there, and it measures, and after sometimes you come back and pick up your instruments and have a registration record of the time series of the current speed and direction for longer time scale. That means that this instrument has to have in it the memory, which you pick up from the current meter. You put it into the computer and read your time series and obtain, in such a way you obtain the data. Current meter, then there are another type of current meter. I won't go too much into details of these things. Then there is acoustic current meter, are based on the principle that sound is compression wave that travels with a medium. Assume an arrangement with a sound transmitter between two receivers in an ocean current. Let receiver A be located upstream from the receiver, and let receiver be located downstream. It bursts. If a burst of sound is generated at the transmitter, it will arrive at the receiver B earlier than at receiver A, having been carried by the ocean current. So you really obtain the travel time of the acoustic signal in function of the current. Electromagnetic and acoustic current meters have no moving parts and can therefore take measurements at a very high sampling rate, up to tens of readings per second. Tens of readings per second. So can you imagine this kind of frequency of measurements. Then we have wave measurements, which are essentially balls which are staying at the surface. They are following these are the wave measurements in the sense that these are the wind wave measurements. You put these balls on the sea surface, and it measures the acceleration of the up and down acceleration of these balls, and the vertical accelerometer measures the buoy acceleration generated by the waves. Then the data are either stored internally for later retrieval or transmitted to shore. So you can have an antenna which transmits all the recorded data to the shore. And this is something which is used quite often for measure the sea surface waves or the wind waves. Let's see, and here we have time measuring the sea level. Okay, these are we have the waves. I would like to repeat it. We have on one hand we have the waves, the wind waves, which are again the variability of the sea level, but variability of the sea level at the very short time scale, at the time scale of 10 seconds. So on the order of 10 seconds. So wind waves have a variability on the order of 10 seconds. So the waves you see when you look yesterday when I was born, you have seen the waves, and these waves have a period of about 10 seconds. But the tide gauges, the tides are also the oscillation of the sea level, but oscillations on the sea level on a time scale on the order of a day. So diurnal, semi-diurnal sea level variations. And these two are the main variability of the sea level of the ocean. If you want to measure the sea level due to the wind waves, we are not interested in tides, because tides are simply the average sea level for wind waves. The tides are moving up and down of the mean sea level. On the other hand, the wind waves, we don't want to have wind waves if we measure the tides. So we have somehow to filter the wind waves while measuring the tides. And this is how one classical tide gauge looks like. So it's a Stilling well gauge, consists of a cylinder with a connection to the sea at the bottom. And this is the connection to the sea at the bottom. And this connection acts as a low-pass filter. Why low-pass filter? Because we don't want to have these waves. So this acts as a low-pass filter, filtering the wind waves, and all the waves of short period cannot pass through. Only the slow change of water level associated with tides can enter the well. So only these slow motion are, and here you have the float, and the float is connected to pen and writes the sea level height on a piece of paper. So it's essentially the analog tide gauge. It's old type analog tide gauge, what has been used until last century to measure tides. And this is, if you remember, one of these of my talks, when I was talking to you about the long-term changes of the sea level, and I said, okay, from satellites we have noticed the long-term increase of the sea level from 1992 up to nowadays. But the same thing essentially has been shown from tide gauges, and these are the instruments which has been used to show the sea level variability on long-term time scale. But they are obviously not covering the open ocean; they are at the coast, and there are a certain number of these tide gauges all around the world ocean, and they essentially shows the same thing: the increase of the sea level. So that's the tide gauges, and they are increasingly used to monitor possible long-term changes in sea level linked with climate variability, as I told you. Okay. So this is these are the classical instruments. Then we have measurements of tide gauges, which measures really the pressure. So you put these kind of pressure sensors, you put it at the bottom of the ocean, and then they measure the pressure, the height of the sea level above the instruments. Because what is the pressure? The pressure is really the weight of the water column, the weight of the water above these instruments. So the higher is the weight, or higher is the pressure, the higher is the sea level. And so you can measure the sea level by measuring the pressure. But here there is a problem. The problem is the following: the pressure at the bottom, or the weight of the water column, or the weight of the water above this instrument doesn't depend only on the sea level height, but depends also on the density below the sea level. The higher is the density, obviously the higher is the pressure with the same sea level. So you have somehow associated with this, you have to have the measurements or the estimates or the vertical distribution of density of the water column above your instrument. Only in that way you are able to distinguish the changes of pressure from the sea level height from the weight of the water column, from the changes of the atmospheric pressure. Here is the final historical notes, what I already told you before. Here is something what I showed you before. This is the Challenger 72-76, and you can see why this ship were doing this such a long time. Departed in 1872 and returned in 1876. So it took 4 years to do this global ocean survey. And that's why, because the ship had to stop every time, do the measurements, and continue its way. Nowadays, it would take only 6 months to do these things, because the instruments are technologically much more efficient, are much faster, they have much faster response, and then the ship can stay for much shorter time in every single position. Here is the reference and reading sources for this for this thing what I have been talking to you as in this first lecture on the instruments. So we have reference and reading sources are of the book of Emery and Thompson, which is the chapter 1, which is data acquisition and recordings, data analysis methods, and in physical oceanography. Because in addition to data acquisition and recording, this is only the first part of the story. The major effort comes later. The major effort is try to do analysis of all these data, because at once upon a time the number of data was relatively small, so it was not such a big deal to analyze the data. But now you are coming with millions and millions of data, because the spatial and temporal resolution becomes higher and higher. Can you imagine that if you for a single lowering of Ctd, you have every second you have two measurements, so temperature and salinity. So for every single lowering of the instrument, you get a huge amount of data, and all these data, so that the data analysis becomes more and more crucial in obtaining synthetic information of what we have been measured. Otherwise, we got lost. We got lost with all this huge amount of data. Then we have another book, which is Oceanographic Instrumentation, an Introduction to Physical Oceanography, which is the book what I gave to you. What you can find also some, and then we have Instrumentation for Physical Oceanography, the last 2 decades and beyond. This is a relatively new book which gives you some overview and prediction how the measurements will be developing. So this is the first first lecture. I will go a little bit ahead, and I will try to start with I will try. Can you see my screen? Yes. Okay, you can see my screen. I will. Okay. So now now we'll pass to the second lecture of this of physical oceanography instrumentation. I will be talking another 10 minutes or something, and then we will continue next three lectures with the instrumentation. And since I don't have any feeling, how can you follow, and do you follow we may want to dedicate the last quarter an hour, half an hour to hear your opinion. What do you think about the course? Do you have any questions as far as a specific subject, what I was treating, or whatever question you have, you will just ask, or I will try to give some questions, get some questions from you. So we are now in the lecture 2, which is autonomous systems. Autonomous systems means that that these instruments are autonomous in the sense that they do not depend for during all time on the action of man. We have moorings, coastal and open ocean examples. Moorings, which means that we anchor a certain number of instruments in the sea, leave them, make them record the oceanographic parameters. Then after sometimes we come back, pick up our mooring, pick up our instruments, take it home, do our analysis, pre-processing, processing, and data analysis. We have towed vehicles, which are vehicles which are behind the research vessels. They are used behind the research vessel. They are anyhow autonomous in the sense that you don't need to have a person sitting on it. Then we have drifters and floats. Drifters and floats are the instruments, as I maybe mentioned or not, they are those instruments which are measuring, which are doing the Lagrangian measurements. Lagrangian measurements, that means that that they are doing the measurements following the currents. They are transported by current, but at the same time they are doing the oceanographic measurements. Then we have autonomous underwater vehicles, which are gliders, and autonomous submersibles, which are the vehicles which are going the underwater, as its name says, and they are autonomous in the sense they are moving by themselves. They don't need to have the man control, in situ man control. Here is the mooring. Okay, let's first talk about the mooring. Moorings are appropriate platform wherever measurements are required at one location or an extended time period. So this is that's the important thing. We are doing the measurements at a single point where we, for some reason, knowing oceanographic processes, we consider this as a crucial points where we need the measurements over an extended time period. We have to, obviously, we cannot place our mooring any place we want. We have to know something. We have to have the hypothesis. We have to have the understanding of the process in order to do our measurements with the moorings. You remember at the beginning of this lecture, I was talking to you. We were discussing the AMOC, Atlantic Meridional Overturning Circulation, and our previous knowledge said us how this overturning circulation looks like. How is the distribution, horizontal and vertical distribution of the current vector? And so we are able, based on our previous knowledge, we are able to design the mooring distribution over for example, 26 degrees north, where we have been measuring the currents. We have been measuring the currents in order to understand the long-term variability of the North or the Atlantic meridional overturning circulation. So we know what are the processes we want to study, and all only then in that case we are able to design an optimal spatial distribution of moorings over over the area. So, the moorings are therefore an appropriate platforms wherever measurements are required to one location over the next extended time period. Or you can have a series of moorings as has been shown, as I show you, in the Atlantic Ocean. Their design, obviously, the design of the distribution of the vertical distribution of instruments depends on the water depth and on the type of instrumentation for which the mooring is deployed. But the basic elements of an oceanographic mooring are an anchor, a mooring line, wire or rope, and one or more buoyancy elements. Buoyancy elements are those which are pushing keeping the mooring in the vertical, the line. So the subsurface, then we have a surface moorings and subsurface mooring. Subsurface moorings are used in deep waters in situations where information about the surface layer is not essential to the experiment. So this again, I will go back to our AMOC pattern, where we have seen that the mooring was subsurface, and we were looking at the measurements in deeper layers in order to help flow. And the main buoyancy at the top of the mooring is typically placed at some 20 to 50 meters below the ocean surface. So this has the advantage that the mooring is not exposed to the action of surface waves, because otherwise it will go up and down. And this is not at risk as being damaged by ship traffic or being vandalized or stolen, because if somebody sees this, they very often they stole it. You can see this figure which shows a typical deep sea mooring. And the main buoyancy is at the top of the mooring line. And to protect the mooring against fish bites, wire is used for the upper 1,000 meters or so. The mooring line, where rope is used below. So below we have a rope, and upper one is the lower is the rope, and wire is upper. At the bottom of a deep sea mooring, just above the anchor, is a remotely controllable release. Because the question is how you would get out this guy from the sea. You cannot, if you don't see it, you cannot determine its exact position, and you cannot come and pick it up. Because here you have more than 1,000 meter weight, which is keeping all this stuff fixed. So in order to get to this mooring, to obtain the mooring at the surface, at the bottom of a deep sea mooring, just above the anchor, this is the anchor, this black stuff here, is a remotely controllable release. It can be activated through a coded acoustic signal. So you send up a coded acoustic signal from the ship, which is up, when it's time to recover the mooring. Triggering the release brings the mooring to the surface, and the anchor, usually a concrete block or a clamp or disused railway wheels, is left at the bottom floor. So this is how you pick up your mooring at the surface, and this is and you need to do this recovery every now and then, because after like 6 months or something, the batteries of the instruments has to be replaced. You have to look at whether functioning of all these instruments are okay, and so forth. So you have to do your control of the mooring every certain period of time, and every time you come with the ship there, you trigger the release, bring the mooring at the surface, and then you copy the data from the instruments, and then eventually you replay or put the mooring at the same location after, and leave it for another period of time. So this is how it looks like. And then there is a surface. If we want to surface layer mooring, we want to surface layer. Sometimes we really need the surface layer mooring, surface mooring, in order to collect the meteorological data. And so we have to have a whole series of meteorological instruments at the surface, and therefore this has to be the surface moorings. So you have the undersurface mooring, or you have a surface mooring. These two are mainly partly for logistical reasons, and partly for the reason of necessity to have the meteorological measurements. Okay, so I will at this point I will stop here. We'll continue the day after tomorrow, and have a good time. And we will be talking about this mooring a little bit more in more details next hours. Okay, so have a good time, and see you soon. Bye-bye.
Bye.
Bye.
Thank you.
Thank you. Bye.